Welcome to the High Voltage AI Podcast.
Great to be here.
We're thrilled to have you join us for another deep dive, especially this Thursday as we continue our week-long series. It's all featured in the PXRD newsletter on Substack.
That's right.
And this week, we've really been immersing ourselves in FERC Order 1920, exploring how it's, well, fundamentally changing transmission design for electric utility engineers.
It really is a sea change.
On Monday, we covered the foundational requirements. Tuesday, we dug into those 7 key benefits reshaping project evaluation. And yesterday, we looked ahead, engineering for 2045, with 20-year planning horizons and scenario-based design.
Really setting the stage for today.
Exactly. Because today, we're shifting focus to a really critical aspect of this whole revolution. Grid-enhancing technologies, your new planning toolkit.
Yeah.
We're going to unpack why these technologies aren't just, alternatives anymore. They're quickly becoming the primary tools for optimizing our existing grid infrastructure.
That's a perfect way to put it. And to kick us off and really underscore the immense potential here, let's look at a real-world example, a big one.
Okay.
When PG&E deployed dynamic line ratings, or DLR, on their 500 kilovolt path 15 transmission corridor, well, they uncovered something truly remarkable.
I remember reading about this. What did they find?
They found that this line, path 15, could actually carry 35% more power than its static rating.
35%. That's huge.
It is, and it could do that during 60% of its operating hours. 60% of the time.
Okay, here's where it gets really interesting, though, right? This extra capacity. When was it available?
That's the kicker. It was available precisely when California needed it most during peak renewable generation periods.
Wow. So exactly when traditional thermal limits would have usually forced massive renewable curtailment.
Exactly. Times you'd normally have to throttle back wind and solar. Instead, they could deliver it.
Incredible. What was the cost versus the benefit there?
Well, the initial investment was around $12 million for weather monitoring control systems.
Okay, $12 million. Seems like a lot, but in transmission terms.
Right, because that $12 million investment, it eliminated the need for a $2.8 billion traditional transmission line upgrade.
$2.8 billion.
Billion. And it also enabled an additional 800 megawatt of renewable energy delivery.
Okay, do the math on that.
It works out to a 233-to-1 benefit-cost ratio.
233 to 1?
Yeah.
That's just staggering.
It is. And this example, I think more than anything, showcases exactly why FERC Order 1920 now mandates utilities to consider grid-enhancing technologies, or GETs, before traditional transmission construction. It's not just theory.
It fundamentally changes the economics. So what does this all mean for you, the engineer listening? Today, we're going to examine the specific grid-enhancing technologies FERC Order 1920 requires utilities to evaluate first.
Yeah, the mandatory ones.
We'll discuss their technical specs, implementation costs, and crucially, those benefit quantification methods that are really revolutionizing transmission development economics.
Right.
Okay, let's unpack this new toolkit, FERC Order 1920's GET requirements, the mandatory consideration framework.
So FERC Order 1920, it's very explicit. Transmission providers must evaluate grid-enhancing technologies as alternatives.
Right. As alternatives to traditional transmission solutions before new construction.
For new construction. Key point.
This isn't optional anymore. It's a mandatory step in the planning process now.
Absolutely not optional. And the order specifically outlines 5 key GET categories that require evaluation. Think of these as the core tools.
Okay, what are the 5?
First, dynamic line ratings, DLR, like the PG&E example. Second, advanced power flow control.
Okay.
Third, transmission switching. Fourth, advanced conductors.
Right.
And fifth, energy storage used as a transmission asset.
Got it. So DLR, power flow control, switching, conductors, and storage as transmission. When utilities evaluate these, what standards do they need to meet? It's not just a quick look. Right?
Well, no, it's rigorous. They have to look at several things. Technical feasibility, can it actually provide equivalent reliability and capacity?
Makes sense. Reliability is key.
Always. Then economic comparison, a full life cycle cost analysis against the traditional option.
Apples to apples.
Pretty much.
Yeah.
Also, the implementation timeline, how fast can you get it in place compared to building new? Speed matters.
Definitely. And operational impacts.
Yes. Operational impact, how does it affect system operations, maintenance, that sort of thing. And finally, regulatory compliance. Got to meet all the technical standards.
Okay. And you mentioned the cost-benefit analysis itself is different now.
It really is. Traditional transmission, it's often a fairly simple ratio, reliability and economic benefits divided by the construction cost.
Right.
The GET framework is broader. It factors in the avoided construction costs, operational benefits, and this really important one, speed benefits.
Speed benefits. That sounds interesting. Explain that.
It literally quantifies the value of getting that capacity enhancement online years earlier than you could with traditional construction.
So you're putting a dollar value on time.
Exactly. Getting that capacity online faster has real economic value, especially with, interconnect queues and decarbonization goals. It's a game changer in the valuation. Dynamic line ratings, DLR, the game changer.
Okay, let's dive into the first one then. Dynamic line ratings, DLR. You said it's often the first step.
Yeah, it's often considered the first logical step, mainly because of those typically very high benefit-cost ratios we talked about, and the implementation risk is generally quite low. It's proven tech.
So what are the technical fundamentals? What's wrong with the old static ratings?
Well, wrong isn't quite the word, but they're very conservative. Traditional lines are rated based on assumed worst-case weather, like 40 degrees Celsius, ambient temp, barely any wind, 0.6 meters per second maximum sun.
The absolute worst day imaginable.
Pretty much. Plus extra safety factors, which means most of the time you're leaving capacity on the table, unused potential.
Okay.
Dynamic rating capability flips that. It uses real-time thermal ratings based on actual weather. Measured ambient temp, wind speed, wind direction, solar irradiance.
Actual conditions right now.
Yes, and even direct conductor monitoring measuring sag temperature directly.
So you're tapping into the actual capacity of the line moment by moment instead of just assuming the worst all the time. How do you implement that? What's involved?
It's a combination of things. First, you need weather station networks.
Okay.
These are meteorological stations usually placed every 5 to 10 miles along the transmission corridor, measuring temp, wind, sun, humidity.
And they send data back.
Yeah, using fiber optic or cellular back to the control centers, usually with redundant sensors, for data quality.
Makes sense. What else?
Then you have conductor monitoring systems. These can directly measure the sag using LIDAR or tension monitors, or use direct temperature sensors on the conductor itself.
So you know exactly how hot the wire is and how much it's sagging.
Precisely. Plus vibration monitoring for things like galloping, ice detection in colder places.
Okay, weather stations, conductor monitors, how does it all come together?
Through control system integration, those real-time rating updates feed directly into the energy management system, the EMS.
So operators can actually use that dynamic capacity.
Exactly. For day-ahead markets, real-time markets, operators get clear displays, automated alerts if ratings change or approach limits. It becomes part of the operational toolkit.
And the economic impact, as we saw with PG&E, is huge. Are those kinds of gains typical?
The percentages vary by region, of course, because weather varies. But based on actual utility deployments, significant gains are common. In the southwestern U.S., you often see 25 to 40% average capacity increase.
Wow.
The Northeast, maybe 15 to 30% typically. The Northwest, usually around 20 to 35%.
Still very significant numbers.
Absolutely. And what's interesting is the benefits are often higher during winter and the shoulder months. Cooler temps, more wind usually.
Right, when you might still have high demand, but better cooling conditions. Let's revisit PG&E Path 15 just to nail down those numbers again.
Okay. The static rating was 3,900 megawatt.
Right.
With DLR, the average dynamic rating jumped to 4,680 megawatt. That's a 20% increase on average.
20% average increase.
But the peak dynamic rating hit 5,265 megawatt. That's a 35% increase.
And that peak, that 35% extra capacity, was available.
First 60% of operating hours, which, as we said, led to avoiding $2.8 billion in traditional construction costs. It's just transformative.
It really is. What about the cost to implement DLR itself?
Yeah.
You said low risk. What about cost?
Relatively low compared to the benefits. Weather stations might be, say, $50,000 to $150,000 each. Conductor monitoring, maybe $100,000 to $300,000 per line segment.
Okay.
The control system integration is often the bigger piece, maybe $500,000 to $2 million per control center.
So overall for a line.
Total implementation cost is typically in the range of $1 to $5 million per 100 miles of transmission line. Compare that to the hundreds of millions or billions for new lines.
Yeah, it's a totally different scale.
Yeah.
How do you quantify the annual benefits then? Is there a formula?
There is, generally. You look at the additional capacity you unlocked, multiply by the hours it's available, times the value of that capacity.
Okay.
Plus, you add in production cost savings from reduced congestion and the value of integrating more renewables.
Can you give a quick example?
Sure, let's say you get 500 megawatt of extra capacity, and it's available for maybe 3,000 hours a year.
Right.
And let's say capacity value is $150 per megawatt day. Just the capacity value component there is about $25.7 million annually.
Wow. Okay, so the payback can be very quick.
Very quick indeed. That's why it's often the first GET to look at. Advanced Power Flow Control. FACTS Technology Overview. Okay, so moving beyond just knowing a line's capacity, the next category is actively controlling power flow. That brings us to flexible AC transmission systems, or FACTS.
FACTS.
Yeah.
Right. These are power electronic devices.
Exactly. They provide real-time dynamic control of transmission power flows. They can be series devices, shunt devices, or sometimes combined, offering, grid-scale optimization, fine-tuning the flows.
It sounds like a more surgical approach than just building bigger lines. What are some key FACTS devices engineers should be familiar with?
Well, a common one is the static VAR compensator, SVC.
SVC, what does that do?
It's a shunt device, usually rated from 50 up to maybe 800 MVAR. The key things are speed and precision. It offers sub-cycle voltage regulation.
Sub-cycle, that's fast.
Very fast. And plus or minus 100% reactive power control. Very efficient too, over 98%.
What are the applications?
Dynamic voltage regulation, improving power quality, enhancing stability, and really importantly, supporting renewable integration by managing voltage swings.
Okay. What's the cost like?
Capital costs are generally $30,000 to $80,000 per MVAR. O&M is pretty low, 2 to 3% annually. And the benefit is often avoiding transmission upgrades or needing extra voltage support from generators. Then you have series devices like thyristor-controlled series compensators, TCSCS.
TCSC, okay, series compensation.
Right. These provide variable series compensation, maybe 0 to 70% of the line reactance. Again, very fast millisecond response to disturbances.
What does that allow you to do?
It gives you continuous control over the line's impedance. You can effectively make the line look shorter electrically, allowing more power to flow. They integrate with protection systems too.
So increased line loading.
Definitely. Can increase loading by 20 to 50%. Also enhances stability, damps oscillations, relieves congestion. Very powerful for bottlenecks.
And the cost for TCSC?
Equipment costs maybe $40,000 to $120,000 per MVAR of compensation. A typical project, say 100 to 300 MVAR, might range from $15 to $50 million total. And then kind of the ultimate FACTS device is the Unified Power Flow Controller, or UPFC.
UPFC sounds comprehensive.
It is highly advanced. It offers simultaneous control of both real and reactive power flow, independent voltage regulation, phase angle control. It basically combines all the capabilities into one device.
Wow. Precision?
Sub-cycle response, and typically plus or minus 1% power flow control precision. Very fine control.
What's the economic case for something that advanced?
Well, if a UPFC can provide, say, a 300 megawatt capacity increase on a constrained path, the annual value from capacity, congestion reduction, stability benefits, it could easily be over $16 million a year.
Okay, so these sound like powerful tools, really fine-tuning the grid in ways we couldn't before. Are there simpler versions too?
Yes, exactly. And that leads to smart wire technologies. Think of them as distributed FACTS or DFACTS.
Distributed, meaning smaller units.
Exactly. Modular power flow control devices. Maybe 1 to 50 megawatt capability per module. And the really neat thing is they can often be installed directly on existing transmission lines, sometimes without even needing an outage.
Installed right on the line, wow.
Yeah. They offer real-time power flow optimization, communicate wirelessly or via fiber, and they're highly scalable. You add modules as needed.
What are the advantages there? Cost, speed?
Both. Lower cost per megawatt of control, maybe $200,000 to $500,000 per megawatt.
Yeah.
Much faster deployment, 6 to 18 months versus years for traditional solutions or large FACTS, and less risk because it's modular. It's almost like plug-and-play grid enhancement.
That DFACTS approach sounds really promising for targeted bottleneck relief.
Optimal transmission switching, OTS.
Okay, this next one, transmission switching. I find this concept really intriguing. Optimal transmission switching, OTS. How does strategically opening transmission lines actually enhance capacity? It seems counterintuitive.
It does seem counterintuitive, doesn't it? But think of it like managing traffic flow on highways. Sometimes closing an on-ramp can actually improve overall flow on the main road by preventing bottlenecks.
Ah, okay. So OTS involves strategically changing the network topology, the connections to optimize power flows.
Exactly. You change the configuration to push power away from overloaded lines onto lines with spare capacity. It can relieve bottlenecks, enhance emergency procedures, and integrate with economic dispatch to lower overall costs.
How is it implemented technically? It sounds complex.
It requires quite a bit of upfront work, detailed studies to understand the impacts of different switching actions. You need adaptive protection systems because the topology is changing.
Right. Protection settings usually assume a fixed network.
Correct. So protection needs to adapt. You also need new operating procedures and, importantly, automation systems that can determine and execute the optimal switching sequence based on real-time conditions.
What kind of capacity benefits are we talking about? Is this proven?
Research and pilot projects have shown pretty significant improvements. PJM studies suggested 5 to 15% capacity increases possible.
Okay.
ERCOT analysis pointed to maybe 8 to 12% congestion reduction potential. CAISO pilots showed 10 to 20% better transmission utilization.
And Europe.
European experience, especially in highly meshed networks, has shown even higher benefits, sometimes 15 to 25% capacity gains.
That's impressive. But I imagine there are significant challenges with operating such a dynamic system. What are the main hurdles?
You hit it earlier. The complexity of adaptive protection is a big one. Ensuring protection systems work correctly under all possible configurations.
Yeah, that sounds critical.
Also, the need for new operator training. They need to be comfortable with a network that changes shape. Rigorous N-1 contingency analysis for all switching states is essential. You have to ensure it's still secure.
N-1 for every state. That's a lot of analysis.
It is. And integrating it smoothly with real-time market clearing systems is another challenge.
Okay, so what's the economic value proposition then?
The benefits primarily come from decreased production costs due to less congestion, increased transmission capacity without building new lines, enhanced reliability during contingencies, and better utilization of variable renewables by routing power more effectively.
And the costs.
Costs are mainly for the studies, the automation systems, and the training. Maybe $500,000 to $2 million for studies, $1 to $5 million for automation, $200,000 to $500,000 for training. So maybe $2 to $10 million total for system-wide capability. Again, much less than new lines.
High temperature, low sag, HTLS conductors.
All right, next up, advanced conductors, specifically high temperature, low sag, or HTLS conductors. This comes into play when existing lines actually need replacement or reconductoring.
Okay, so this is about upgrading the wire itself. You're not just replacing like for like, you're putting in something much better.
Exactly. It offers a significant capacity increase, often using the existing towers and structures.
That's a huge advantage avoiding new rights-of-way.
Yeah.
What are the main technology options for HTLS?
There are several types. A common one is ACSS, aluminum conductor steel supported. That typically gives you about a 25% capacity increase.
Okay.
Then there's ACCC, aluminum conductor composite core. This one uses a lightweight composite core and can offer a much bigger jump, 50 to even 100% capacity increase.
Double the capacity on the same towers.
Potentially, yes. There are also gap-type conductors designed to manage thermal expansion differently, and specialty alloys for really extreme temperature or environmental conditions.
What makes them perform so much better? Higher temperatures.
That's the main thing. They can operate at much higher temperatures, think 150 to 250 degrees Celsius, compared to conventional ACSR, which is usually limited to 75 to maybe 90 degrees Celsius.
Wow, much hotter. Doesn't that cause sag problems?
That's the low sag part of HTLS. They're engineered to show minimal sag increase even at those high temperatures. This means you can push much more current through them.
How much more current?
Typically 1.5 to 2.5 times the current capacity of an equivalent conventional ACSR conductor.
Plus lower losses.
Yes, another benefit. Because they often have lower resistance at operating temperatures, you get a 15 to 30% reduction in line losses, saving energy while delivering more power.
So you're not just upgrading capacity, you're really transforming the line's fundamental capability. What's the catch? Cost.
The conductor itself is more expensive, yes. Maybe 1.5 to 3 times the cost of conventional ACSR. And installation can be a bit more complex, adding maybe a 10 to 25% premium there.
But compared to building a whole new line.
Exactly. When you factor in avoiding new rights-of-way, new towers, long permitting, reconductoring with HTLS typically achieves a 3 to 8 to 1 benefit-cost ratio compared to building a new line for the same capacity increase.
That's a strong economic case. And can these integrate with real-time monitoring, too, like DLR?
Absolutely. You can install conductor monitoring systems for sag, temperature, tension directly on lines with HTLS conductors. This data can feed right into dynamic line rating systems, giving you real-time capacity adjustments based on the actual state of the advanced conductor. Plus, predictive analysis, automated alarms for thermal or mechanical limits. It all integrates for smarter operation. Energy storage as transmission. Battery and pumped hydro. Okay, the fifth category FERC highlights is energy storage as transmission. This focuses on using utility-scale batteries or pumped hydro specifically to provide transmission services.
Right, not just storing energy for later use, but acting like a transmission asset itself. How does that work with batteries?
We're talking about transmission-connected battery storage. Typical installations might be 10 to 300 megawatt, with maybe 1 to 4 hours of energy storage duration.
And their role?
They offer incredibly fast response millisecond level for grid services. A key one is congestion relief. Charging when the path is clear, discharging when it's congested to effectively increase the path's transfer capability.
So smoothing out the peaks and valleys on the transmission line itself.
Exactly, plus providing voltage support, frequency regulation, and importantly, transmission deferral. Installing a battery might let you postpone a costly line upgrade for several years.
And the value proposition for storage as transmission is really multifaceted then, isn't it? It's stacking benefits.
It absolutely is. The value includes that transmission deferral value, potential revenue from relieving congestion, revenue from ancillary services like frequency regulation, and possibly capacity market revenue as well. It's a complex calculation, but potentially very valuable.
What about pumped hydro storage? That's an older technology, but still relevant here.
Very relevant. Pumped hydro storage involves large-scale installations, usually 100 to maybe 3,000 megawatt, much longer duration too, 6 to 20 hours of storage typically.
What transmission services can pumped hydro provide?
It offers significant inertia, which is crucial for grid stability, especially with more inverter-based resources like solar and wind. It provides stability services, voltage support, and even black start capability, the ability to restart parts of the grid after an outage.
Are there advancements in pumped hydro too?
Yes. Advanced pump storage units now feature variable speed turbines and pumps, offering more flexibility. There are also ternary units that can operate in pumping, generating, or synchronous condensing modes for reactive power support. And new designs explore underground reservoirs or using seawater for coastal installations. So it's an evolving technology too. Implementation economics and payback analysis, comparative economics.
Okay, let's put this all together from an economic perspective. We've talked about the potential, but let's compare the GETs directly against traditional transmission. What's the real difference in cost and time?
It really is a stark contrast. Let's take a hypothetical new 230 kilovolt transmission line, maybe 100 miles long.
Okay, pretty standard project.
Typical cost these days, $1.2 to $2.5 million per mile. So that 100-mile line is costing you $120 to $250 million.
Right. And the timeline.
This is key. It typically takes 7 to 15 years to develop and construct something like that. Permitting, rights of way, construction, it's a long haul. And it might add, say, 500 to 1,500 megawatt of capacity.
Okay, 7 to 15 years, $120 to $250 million. Now compare that to the GETs we've discussed. DLR first.
Dynamic line ratings. Capital cost, we said $1 to $5 million per 100 miles. Implemented in 1 to 2 years, adds maybe 15 to 40% of the existing line capacity. And that typical benefit cost ratio, 10 to 50 to 1.
Huge difference. Okay, FACTS devices.
FACTS devices. Capital cost maybe $15 to $50 million per installation. Implemented in 2 to 4 years. Could add 20 to 50% capacity on a constrained interface. Typical benefit cost ratio, 2 to 8 to 1. Still very favorable compared to the new line.
Much faster, much cheaper, still good returns. What about the risk factor? These are newer technologies for some utilities.
That's a fair point. We need a risk-adjusted analysis. DLR is generally considered low risk now. It's proven, widely deployed.
Okay.
FACTS devices are maybe medium risk. The technology is mature, but utility experience varies and integration can be complex.
Transmission switching.
Transmission switching, I'd say, is medium-high risk currently, mainly due to the limited operational experience and the complexity of adaptive protection and operations. Needs careful piloting.
And advanced conductors.
Low-medium risk. The materials are proven, but installation requires specific techniques and expertise compared to conventional conductors.
So how do utilities mitigate these performance risks when they're relying on GETs instead of building a traditional line?
There are several ways. Pilot programs are crucial, especially for newer tech like OTS, to gain experience in a controlled way.
Smart.
Securing vendor guarantees on performance, using insurance products where available, and importantly, maintaining fallback plans. Maybe having traditional transmission alternatives identified if a GET solution significantly underperforms expectations. It's about prudent planning, regulatory and market integration, FERC Order 1920 compliance.
This isn't just about the tech itself, though. It's about how it fits into the whole regulatory and market structure. What does FERC Order 1920 actually require utilities to show when they propose a GET solution?
Right, compliance is key. The order imposes specific documentation requirements. First is technology screening. Utilities have to show they evaluated all applicable GET technologies for the identified need.
Can't just pick one favorite.
No. Then, the economic comparison, we discussed that detailed benefit-cost analysis comparing the GET to the traditional solution, including those speed benefits.
Good.
Third, technical feasibility. They need engineering studies demonstrating the GET can provide equivalent performance and reliability.
Proof it works?
Yes. And finally, a clear implementation plan timeline, milestones, how they're actually going to deploy it.
And stakeholder involvement is a big part of FERC processes. How does that fit in with evaluating GETs?
It's absolutely integral. The process includes public input through formal comment periods on the utilities plans.
So transparency.
Yes. Often technical conferences are held to educate stakeholders on GET capabilities and the specific proposals. Sometimes independent third-party review of the utilities evaluations is required or used.
Adds credibility.
Definitely. And ultimately, the state or regional utility commission needs to approve the GET implementation plan and its cost recovery.
Okay, so once a GET project is approved and built, how does it actually integrate into the existing electricity markets, both for long-term planning and day-to-day operations?
Good question. In transmission planning markets like the regional planning processes, GET solutions will now compete directly alongside traditional transmission projects.
Okay.
This means establishing clear performance standards for GETs, figuring out cost recovery mechanisms often similar to how traditional assets are treated, maybe with rate base inclusion, and potentially incentive structures to reward GETs that perform effectively.
And in the day-to-day operational markets?
In operational markets, GETs become active participants. DLR provides real-time capacity limits. FACTS devices and storage can bid into ancillary service markets.
Like frequency regulation.
Exactly. Their operation will influence congestion patterns and therefore financial transmission rights, FTRs. They'll be dispatched as part of transmission constraint relief procedures, and they'll need to be compensated for the reliability and stability services they provide. It requires integrating them fully into market software and operations. The bottom line for transmission engineers.
So wrapping this up, it seems clear that grid-enhancing technologies are, well, they're much more than just minor alternatives to building new lines. They're rapidly becoming the primary go-to tools for optimizing our existing grid infrastructure, even while we continue to plan and build necessary new large-scale transmission.
It's really a shift in thinking, a new toolkit, as you said.
For you, the transmission engineer listening, what are the key takeaways? The implementation priorities based on what we've discussed.
Okay, boiling it down, I'd say. First, start with dynamic line ratings. Seriously consider DLR first. Highest benefit-cost ratios generally, lowest implementation risk. It's the logical starting point for most utilities to unlock hidden capacity.
Okay, DLR first, then what?
Second, evaluate FACTS for constrained interfaces, where you have persistent known bottlenecks. Things like series compensation or power flow controllers can provide immediate targeted relief.
Makes sense. Address the known problems.
Third, consider advanced conductors for reconductoring. When those existing lines are due for replacement anyway, using HTLS conductors is a massive opportunity to get significant capacity increases relatively cost-effectively. Don't just replace like for like.
Leverage that rebuild opportunity.
Exactly. Fourth, pilot transmission switching carefully. Given the operational complexities and limited experience, OTS needs careful, well-designed pilot programs before you rely on it system-wide. Learn before you leap.
Prudent approach. What about storage?
Fifth, integrate storage strategically. Transmission-connected storage offers multiple valuable services, but it requires careful economic analysis considering all those potential value streams, transmission deferral, ancillary services, congestion relief. It's not always a simple case.
Means a holistic view.
Yes. And finally, plan for portfolio solutions. Don't think of these as isolated tools. Often, the best approach is combining multiple GET technologies, maybe DLR, plus some targeted FACTS for a really comprehensive transmission enhancement strategy.
That makes a lot of sense. It's not just about having new tools, it really is about a new mindset for grid planning and operation, embracing optimization and flexibility.
Precisely.
So, a question for you listening. What grid-enhancing technologies is your utility evaluating or deploying right now? Have you seen successful implementations of DLR or FACTS devices that really changed the game locally? We'd love for you to share your experiences with GET economics and performance.
Yeah, hearing those real-world stories is invaluable. And tomorrow, just to wrap up our week on FERC Order 1920, we'll look at the career side.
Right. How are these changes creating new engineering opportunities? What skills are utilities looking for now? And what are the career development paths for engineers in this evolving transmission industry?
Understanding those career implications is really important for positioning yourself for the future.
Absolutely. It helps you navigate where the industry is headed.
So if you'd like to leave feedback on today's deep dive or have any questions, feel free to reach out. I'm at emma.quinn.power.podcast@gmail.com.
And I'm at alex.reed.power.podcast@gmail.com. Thank you so much for joining us today. Until tomorrow, keep learning and innovating.